Hello friends, welcome back to this series where we work through the book on quantum mechanics by Steven Weinberg. In this video, we shall go over the solutions to the exercises given in lecture 24. That's the lecture where we discuss the Wigner-Eckart Theorem, which has everything to do with the rotational symmetry of a quantum system. For the first exercise, we ask you to prove an operator equation that one frequently encounters in symmetry transformations like rotations. We use the spin J operator, OJM, as an example, but basically any operator in Hilbert space is rotated by this unitary transformation. J is the angular momentum generator of rotations. This is the standard form for the symmetry transformations of operators, where the operator to be transformed is sandwiched between the unitary operator that represents the symmetry and its Hermitian conjugate. We have discussed this standard form in lecture 4 extensively. This is known as the Heisenberg's picture of symmetry transformations. The link to that video is in the description. We claim that this rotation is actually equal to this linear transformation. Your task is to prove this relation. Let me remind you what this exponential on the right-hand side means. Just do a power series expansion. And what we mean by this notation is nesting the commutator around the target operator, which is the operator we are transforming, n times. In order to prove this relation, the hint is to expand this modified expression as a power series in terms of lambda, then remembering to set lambda to 1 in the end, so that we get an infinite series which represents the left-hand side. Let's look at the power series expansion. Evaluating this coefficient should be instructive. This is the first-order derivative. The derivative with respect to lambda only acts on the two unitary operators sandwiching OJM and is equal to the following through the product rule. Since the operator being transformed could be any operator, let's replace OJM with just a placeholder. Let's set lambda equals to 0 only at the end and ignore this condition for now. The derivatives of the exponentials are given by Note that phi dot j commutes with the exponential, so it could be placed on either side of the exponential. Our choice of this particular ordering is because this will lead to the following neat result. Which is just the commutator of phi dot j with the operator being transformed. We then end up with this recursive relation. As you can see, we started with an operator sandwiched by u dagger and ended up with another operator which maintains the same standard form. This new operator is just the original operator inserted into a commutator with phi dot j times a factor of minus I over h bar. The preservation of this standard form implies that with each subsequent lambda derivative, we will simply get another layer of commutator times an additional minus I over h bar. we can simplify the notation for n nested layers of commutator. And finally, setting lambda to 0, all the exponential operators become the identity operator. Let's put back the operator OJM. These are the coefficients of the power series in lambda. And we recognize this as the power series expansion of an exponential function. Then finally, setting lambda to 1. Thus we have proven the identity we have set out to prove. This identity is very useful when studying symmetry transformations once you know the commutation relations between operators, as can be seen on the right-hand side of this equation. For the next exercise, we deal with a specific example of the spin J operator when J is equal to 1. This is a set of operators that correspond to m equals -1, 0, and +1. We can see this as a vector operator expressed in the spherical basis as we have explained in lecture 24. In the same lecture, we have worked out the commutation relations of these operators with J3 and J ±, the generators of rotations. It is precisely these relations that define the spin J equals 1 operator. Our task is to find the representation of this operator in a different basis, the Cartesian basis. The components in this basis is related to those in the spherical basis by a linear relation, where the omegas are numerical constants. These components should satisfy the commutation relation in the green box, which governs how Cartesian vector operators transform under rotations. Use the commutators of the spherical components to demonstrate this, and find the exact relation between the Cartesian and spherical components. Let me remind you that we are using the Einstein's convention, where repeated indices are summed over, as can be seen in these relations. For a start, let's express the Cartesian components of J itself in terms of J ±. The third component of both the Cartesian and spherical bases is J3, and these are the Cartesian components of J. Since J itself is a vector operator, then are these precisely the relations between the Cartesian and spherical components that we are looking for? It's close, but not quite. As we shall see, J ± differ from the spherical components of J by just some normalization constants. We shall see what this means in a minute. Let's first work out the commutators between the Cartesian components of J and the spherical components of V. Then later, take the appropriate linear combinations to reproduce the Cartesian commutation relation in the green box. Let's start with V0. Now we use the spherical commutation relations from earlier to evaluate this commutator. From the expression for J1 above, it will be convenient to multiply this by 2 if we wish to express J1 in terms of J ±. This relation in the red box will allow us to evaluate both of these terms. Now for the commutator between J2 and V0. Again, from the definition above, we should multiply this by 2i. Once more, the relation below allows us to evaluate this commutator. Notice that this differs from the above result by just a minus sign. Hence we get Now look at this relation in the red box. If we identify V0 in the spherical basis as V3 in the Cartesian basis, this will exactly be equivalent to the Cartesian relation in the green box, since the epsilon symbol is 0 whenever any two of its indices are equal. This is our first result, which is rather trivial. Now let's focus on the two relations above. Dividing the first equation by 2, we have the left-hand side is already the commutator between Cartesian components, since V0 is just V3. Therefore, in order to satisfy the constraint in the green box, the right-hand side must be proportional to V2. This corresponds to ijk equals 132, with the epsilon value of -1. So we must define the expression in the yellow box to be V2, in order to satisfy the equation in the green box. Now let's look at this second equation. Dividing by 2i, we have. If this expression in the yellow box is defined as V1, the relation in the green box is once again satisfied. So far, using only 3 equations from the green box have already allowed us to define the Cartesian components of the vector operator V in terms of its spherical components. By right, the blue box would then be the solution to this exercise. But there are a lot more equations in the green box. Are they all satisfied by the solution in the blue box? We need to check this. For example, the commutator between J1 and V1 must be equal to 0, according to the green box. Is this true for the blue box? Let's substitute the expression for V1 in terms of the spherical components. Since we are expecting this to be 0, let's just look at the proportional expression. Again, the spherical commutation relations will allow us to solve these commutators. We will also need J1 and J2 in terms of J plus minus. These two commutators have the following generic form. And expressing J1 in terms of J plus minus. To evaluate this, we need these 3 relations in the red box. Notice that we get the same result for V plus 1 or V minus 1. Therefore, these 2 terms in the yellow box just cancels each other. So indeed, J1 commutes with V1. It would now be convenient for us to check this equation, whether J2 commutes with V2 as defined in the blue box. Expressing J2 in terms of J plus minus. Let's break this up into 2 parts. We would need the same 3 spherical relations in the red box as we did for the commutator of J1 and V1. Recall that this relation simply means that the +1 component of V cannot be raised any further, nor can the -1 component be lowered. Thus these are the non-zero parts of these two commutators, which, according to these two relations below, are equal and should cancel each other. J2 really does commutes with V2. Next, we could try to verify these two very similar relations. According to the expressions of the first and second components in terms of the spherical components of both J and V, these two commutators are composed of the following generic terms. Note that because we are dealing with commutators between either J1 and V2 or J2 and V1, these two signs are always the same. Let's now focus on this generic term. This is equal to the following non-zero terms, again according to this spherical relation below. These two commutators have the same value. Let's go back and apply our result to these two commutators. Let's start with this commutator first. Multiply by 2 so as to express J1 in terms of J plus minus. Then using the solution for V2 and applying the green box, now for this commutator, and applying the result in the green box. We have this result. It is easy to check that these two equations are consistent with the Cartesian commutation relations in the green box. Now we are left with the last two commutators that we have to check. Let's put all the relevant constant factors up front. These two commutators are encapsulated by the following generic term. Referring again to the spherical commutation relations, we have the following. The green box provides the solutions to the two commutators above. The first one can be written as, and we recognize that the term in the red box is just V2. Now for the second commutator, this can be written as, and the term in the red box is just V1. Once again, it is easy to verify that these agree with the commutation relations in the green box. Thus we see that the solution in the blue box does indeed satisfies the commutation relations for Cartesian vectors. This concludes the solution for exercise 2. There's one further point we would like to make before moving on to the next exercise. Let's first invert these relations to express the spherical components of V in terms of the Cartesian components. Taking the sum of these two equations, we have. This gives us V minus 1. Then take the difference, which gives us V plus 1. V0 is just V3. Compare this with J plus, J minus, and J3. Are these the spherical components of J? As you can see, J plus minus differs from the standard form of the spherical components by just some constant prefactors. This is what we mean when we say that the components in the blue box are spherical up to normalization. It is important to note that since J is both the generator of rotations and a vector operator, it must thus satisfy the Cartesian commutation relation in the green box, which is just the algebra for rotation generators. This implies that we can construct the actual spherical components for J simply by using the recipe above. And these would naturally satisfy the commutation relations for spin 1 operators. Note that if we were to use the blue box instead for V in the red box, even though the constant factors in these commutation relations would have to be modified, the same operators will still be related to each other. In this sense, the prefactors of the operators can be viewed as normalization constants. Now we move on to the last exercise. This one's about constructing spin J operators out of spherical harmonics, where J takes integer values. This is what we should expect from these functions, since they are angular momentum eigenfunctions with integer value quantum numbers. The functions YLM depends only on the direction of the position vector, which is defined by the unit vector x hat. Recall that a spin J operator is defined by this set of commutators. The claim is that the spherical harmonics would satisfy this set of commutators if we replace its argument with the operator counterpart, where the position vector is replaced by the position operator. In lecture 24, we have already gone through how you could prove the first of these relations using the properties of the spherical harmonics. For this exercise, you will need to prove the second relation. And as before, you can do this using the properties of the spherical harmonics. Let's see how this works. We first start with this equation. This is how an angular momentum state is transformed by the angular momentum ladder operators, L plus minus. Let's turn this into an equation about the spherical harmonics. We do this by taking an inner product with cat x. This term on the left-hand side is basically how the operator L plus minus acts in position space on the state Lm. State Lm in position space is just the spherical harmonics. The position space representation of L plus minus can be obtained simply by substituting the position space representations of position and momentum operators into the definition of L plus minus in the blue box. We have covered the position space representation of these operators way back in lecture 2. See the link in the description. Let's proceed with this substitution. First start with each component of the angular momentum. Then plug this into the definition of L plus minus. An important point to note, and this is something we will use later, is that L plus minus depends linearly on position and momentum. This is quite obvious, since the angular momentum is linear in both these variables, and L plus minus itself is a linear combination of L1 and L2. So the term on the left-hand side of this equation is just the position space representation of L plus minus, which is some differential operator acting on the spherical harmonics YLM. Let's convert this into an equation about operators in Hilbert space. As mentioned before, this is done by replacing all the position vectors by their operator counterparts. Note that the derivatives, which are previously derivatives with respect to number variables, are now derivatives with respect to operator value variables, which is the position operator. Now let's see how commutators enter the left-hand side of this equation. Let's take a closer look at this differential operator, which can be written as: we can take this minus sign out of the argument and move it in front. This is possible because, as mentioned earlier, L plus minus is linear in momentum. Recall the canonical commutation relation between position and momentum operators. This has the implication that the commutator of any function of x with p is equal to the derivative with respect to x. We have derived this in lecture 2 in connection with what we have called the product rule for commutators. Check out that video if you are unfamiliar with this result. The link is in the description. This equation in the green box is key. Look at this term in the red box. We claim that this can be written as the following commutator. This works by applying the relation in the green box to the derivatives in L plus minus. The function f is YLM in our case. And this works precisely because L plus minus is linear in momentum p, while at the same time YLM commutes with x. Let's quickly see why this is true. L plus minus is given in the curly braces. We can write these two derivatives as commutators using the green box. And because YLM also commutes with x, xj can be moved into the commutator right next to pk. We can do the same for the second term. Then combining these two terms back into L plus minus. This is the result we claimed earlier. Let's hide the arguments of L plus minus to keep things simple. Thus we have the result that we are trying to prove. And this is possible just from the rotational properties of the spherical harmonics. The set of operators YLM is indeed a spin L operator. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.